It's the last unit, Unit 10. Oh my gosh, I'm so excited. Unit 10, finally. That means the year's coming to an end. That means the crazy review starts. That means you should subscribe to my YouTube channel, and I will tell you why. Make sure. Oh, and I was gonna get this set up beforehand. Make sure. Let me do this real quick. I'm gonna switch to my school account. If you go onto YouTube and you search for me, I don't come up right away because I'm not your highest priority. If you search for me and you click on any one of my videos, let me get rid of that. But if you see down here, see this bell? If you click on this bell, what you'll find is as soon as I post a review video or review notes or something, or if I'm going to go live, I'm going to try to do some live review sessions, live, what do you call them? YouTube live review sessions this year. If I'm going to go live, you'll get a little notification. Hey, Mr. Krause is going live. Give me an opportunity. Maybe ask some questions. You might just want to watch the YouTube live session later, but you can also get notification that I am, in fact, going to go live. Hopefully it works. I'm crossing my fingers. We'll see. First time I'm trying it. You know who's going to help me? My Dunkin Donuts coffee. For those of you that make fun of my Dunkin Donuts coffee, I don't care. Leave me alone. Do you know there's actually people that don't like my humor? They're like, in the comments go, Mr. Krause, you're a pretty good math teacher, but your comedy, NK Infinity, is really awful. Duh, I'm a math teacher. I know my comedy's awful. Let's get going. All right, kids. This unit's gonna be a little bit heavy for you. This is stuff that normally would have been taught in AP Statistics, and instead we're gonna do it in Algebra 2 because New York State decided instead of teaching trigonometry in an algebra course, which would have made a lot more sense, we're going to do statistics because that makes more sense. But so today we're going to talk about sampling distributions. Today is all about getting the notation down, getting the basic understanding down, of trying to understand what all this stuff means, what all the different symbols mean, and a little bit about sampling and the distributions and what they look like. We're going to be using the TI Inspire quite a bit, so hopefully you have a copy of that, or hopefully you have that. If you don't have that, you're just going to kind of have to watch. And if you have that, I would suggest you work along with me, okay? So let's get started. All right, so some of this stuff is a little bit similar to things we've done in the past, and some of it is going to be completely and totally new. Population. All right, so what is population? It is, I thought I was in red, a set of measurements. I want you to think about this as being the universe. And I know you've probably heard me say that before. Think of this as, I'm trying to write neat because I got kids at my school that are complaining about my penmanship, as the universe. It's everything. Everything. And it's the universe for whatever we're interested in. Whatever we are interested in. So if you wanted to think about, now population doesn't have to be like everybody thinks it's got to be it's got to be as big as the population of the United States. Yeah, the population of, if I wanted to do for the last presidential election, Trump versus Clinton, I could survey the entire population of the United States, but that would be everybody. Now, in that case, the universe wouldn't be everybody. it would be everybody that was of voting age and had registered to vote. Because if you're not registered to vote and you're not of voting age, it really doesn't matter what you think, because you have no determination on the election. So if my sampling was for the election, my population would be everybody in the United States that was of voting age and registered to vote. That would be my population. Or let's take a smaller example though. Let's say I just wanted to find out what percent of your school's students have an iPhone. Well, the population would be all the students in your school. Now, it doesn't matter if they own a phone or not. It is all the students in your school. So an example of this, let me give you an example. I'll just write this one out. We want to know what percent of your school's students own a crappy iPhone. I'm not an iPhone fan. Just bought a Samsung Galaxy S8. Quite happy with it. I like to be able to tinker. Apple's it's like user friendly, which I don't like. I like to be able to tinker with my toys. So what percent of your school students own an iPhone? Okay. So the population then would be all students in the school. All students, whether they own a phone or not, it would be all students. If you said what percent of students that own phones own an iPhone, that would be changing the dynamics of your population. In that case, you'd say, okay, let's just find out, do you own a phone? Yes? What kind of phone is it? Oh, it's an iPhone. Check. Oh, it's a Samsung. Oh, check. Oh, it's a Huawei or whatever those other ones are. Check. And then you'd find out what percent. Actually, in this case, excuse me, I probably misspoke there. Because we're dealing with sampling distributions today, in this case, we're talking about parameters. What we want to find out is, do you own an iPhone or do you not own an iPhone? So in this case, it would be a yes or a no. And you'll see what we're talking about in later. We're not talking about means today, although we are going to discuss it a little bit. Okay, the sample then should be relatively obvious. It is a subset. It is a subset, and that's the most important piece there, or subset of, the population. It is a subset of the population. And then this is what we have selected to analyze. Have selected to analyze. So in Unit 8, we discussed how to sample. We discussed how to get a good random sample that we try to eliminate bias. So in this case, nobody really would be biased to say, oh, I own an iPhone, or oh, I don't own an iPhone. Maybe there's a little bit of bias there, I guess, by asking kids. But the population, go back to our example. Let me give you IE here. In our example here, we asked students what kind of iPhone they had. Now, well, I could go around and I don't know about your school, but our school's got almost 1,500 students in it. First of all, that would take me almost forever to do. Not forever, but it would certainly take me a long time. So what we would do is take a simple random sample. Simple random. We'll be calling this an SRS later. Simple random sample. Of a select group of people. Now, maybe I said that not quite correctly. it has to be a random sample. You can't just say, oh, okay, I'm just going to pick from these kids. You have to set up a thing. For example, I could stand at the front of my school and I can just point to a number on my paper and I say, oh, I'm going to pick the fourth person. And then I'm going to pick every ninth person after that and say, okay, the fourth person that walks by me, I'm asking them what kind of phone you own. And then I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 kids past me. The ninth kid, I asked, what kind of phone do you own? And then ninth kid after that, ninth kid after that. And then you also decide, okay, I want to select a certain number of people. So then you'll say, let's say I want to select 30 people. 30 is usually a good number to pick. I want to pick 30 people, and that will give me a large enough sample size that I can start making predictions. Now, naturally, this is important. Naturally, this will not be exactly the same as the population. Okay, because that makes sense, right? If you surveyed everybody, you'd get the exact mean and the exact standard deviation and all that good stuff. But by taking a sample, you're trying to say, okay, I'm not going to get it exact, but can I, first of all, get a good random sample, and can I take a large enough sample size of size n, whatever n is, 30, 40, 50, whatever you decide is necessary, to get a really good idea about what's going on in the population. And that's what statistics is all about. Not sampling everybody, because first of all, that's way too expensive, way too time consuming. And you don't get that much better results by interviewing everybody. By taking a sample and running some good sample statistics that we're going to talk about in this unit, then you can get a really good prediction. And how good that prediction is what we're going to be talking about a lot over the next 8 days. Okay, so I'll be back. Okay, so let's talk about what this day is all about, because I believe this day is called sampling distribution. So there is the definition of a sampling distribution. Let me get to red. I like red better. So it is. I'm going to read this one so I make sure I get it right. It is the distribution. Why did I not get to red? Red. The distribution. It's a smaller pen. Of statistics of every possible sample of the desired sample size n. So there's my sample size n. All right, and we're going to discuss what this means at length, but here's what I'm talking about. Let's say my population is all the students in Hilton High School. That's my population. My sample might be a group of 30 kids. But think about this. If I take a sample of 30 kids, I'm going to get a mean and standard deviation of those 30 kids. And let's say your friend does a sample of 30 kids. She's going to get a mean and sample and a standard deviation. It's going to be slightly different than yours. And it'll be slightly different than the population. And let's say I had all the kids in my Algebra 2 class. We're going to do a sample of 30 kids and 30 kids and get the mean and the standard deviation. Everybody's would be slightly different. Right? But if you take all of those samples and put those into those are all part of the sampling distribution. So what you'd have to do is, let's say our size was n. We'd have to take all possible combinations of size 30 of the population. which again would be sort of kind of difficult. But we're going to try to figure out how we can do that effectively, get relatively accurate information, but not spend hours and 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 tons of money doing it. All right, so numbers deal with, we got this thing, parameters. This is a parameter, and this is important that you understand it, is a value associated with associated, man, those just keep wanting to combine, with the, and put it in bold letters, population. Parameter. When I talk about a parameter, I am talking about the population. We often don't know much about the parameters because we can't possibly know what all people of every person in the population knows or thinks or what they believe or whatever. So we are always trying to get close to the parameter. Parameter. And why? Well, as it is the, and I'm going to put this in bold letters, it is the truth we are seeking. Through sampling. And let's just call it the overall truth. So what I mean by this is this. The parameter deals with the population. We are going to do sampling to try to get as close to the actual parameter, which we may or may not actually know. That's going to be a kind of a weird topic for many of you. We're not going to actually know what the parameter is, but we're going to be so careful with what we do that we know whatever answer we come up with is as close to the truth as possible, because the parameter is the actual truth. Now, again, do I know the average age of males that play backgammon? No, I don't. But I probably could figure out a way to sample and figure out, okay, I get close. That's a dumb example, but whatever. Do I actually know? I don't know. There's, we'll be doing so many different examples of, do we actually know the number of pairs of jeans all the kids at the high school own? No, I have no idea how many jeans kids at high school owns, or how many pairs of leggings or jeggings or whatever those things are called that girls own. Don't possibly know, but I could do some sampling and figure out, okay, let's say the mean, the overall truth was, that girls owned 4.8 pairs of jeggings, which, we'll just use that as a number for now. That's the overall truth. Well, we got 4.75. Well, okay, we were pretty close to the overall truth. How close were we? Well, we don't really know what the overall truth is, but we're going to talk about confidence and how confident we are that we're really close. We'll come to it. What's going to come? A statistic is a value associated with a sample. A value associated with a sample that we take. It is an estimate of the parameter. So we're always trying to get our statistic as close to the truth, the parameter being the truth, as we possibly can. All right, so let's go back and let's go remind ourselves of a few things that we know before, and then some new stuff. But before we do that, we need time to have a Dunkin Donuts discussion. You're too young for Dunkin Donuts, but when you get older, ooh, it's so delicious. Gotta love Dunkin Donuts K-Cups in the morning. All right, so we've done these before. We've talked about X bar being the mean. Remember, this is red X bar. The parameter would be the symbol mu. It's red mu. The standard deviation for a statistic is S, and for the parameter, it is sigma. And the variance is the standard deviation squared, or sigma squared. And the proportion, in this case, would be p hat for the sample. And for the parameter, it would be p. Proportion stands for p, not probability. It stands for proportion this time. Now, proportion means, if we're talking about, like, for example, in your classroom, what proportion of the students in your classroom are girls and not girls? As opposed to what's the average number of girls, which I don't know if you'd ever do that. You wouldn't do that. But instead of taking a mean, we take a proportion. So there's proportions deal with kind of yes-no questions, whereas means deal with, like, what's the average shoe size of girls in your class, or something to that effect. All right, population. When we're talking about the population for means, we're talking about mu. Overall sum divided by total. I don't know. Oh, well. Yes, that makes sense. But if we're talking about the sample, it's X bar, right? So if I wanted to find out the average of the test scores, I'd add up the total. Obviously, the total is however many kids you got times, 100, or however, whatever the test is out of. And then you add up all the kids' test scores. That's the sum divided by the total. That gives you your mean. This is means. If I was talking about proportions, now proportions are completely different things. Notice this is the total number of yeses divided by the total. So again, let's go back to the example of girls and boys in your classroom. What you walk up to is, this is how it works. Let's say there's 30 kids total in your classroom. Well, you don't have to actually walk up and say, are you a girl? Are you a girl? Are you a girl? For the most part, you can probably look out and go, girl, 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 girl. There are, yes, there are, or, you almost have to think, I went to this person, I said, are you a girl? Yes. Boom, yes. So a proportion is the number of yeses divided by total. That's different than taking up there and finding a decimal percent, or a decimal average. So in the population, again, this is P. In the proportion, it's P hat. We're going to be doing mostly with proportions today. So let's think about this. I want you to take a couple seconds. You can pause the video if you like. Look at these examples. And I would like you to tell me whether or not you think they are a proportion, or a parameter, or a statistic. Are they a parameter or a statistic? Are they dealing with the entire population, or just a sample of the population? So if you paused it and now you're back, welcome back. So I'm looking at this number right here, 9.3. So it said, the Bureau of Labor Statistics interviewed 20,000 Americans and determined that 9.3% were unemployed. Well, clearly this is a statistic. And it is a statistic because this 20,000 is not all the people that work in the United States. So it is a sample proportion. By the way, this is, and did I tell you that? I should have probably asked you for whether or not it was a proportion or not. But this is a proportion. Now, why is it a proportion, and not a mean? It's not, it is a proportion because I said, do you have a job? Yes. Do you have a job? No. Do you have a job? Yes. It's not how long you've been working or how many years you've had a job. That's a different story. That would be means. This is a proportion. We're going to be using those interchangeably, not interchangeably, but we're going to be using them, and you have to be able to go, okay, that's a proportion, yes and no. That's a mean, I'm going to get an average. The fair farm is very picky about their oranges. The mean weight of the oranges is known to be 12.3 ounces. Before the last shipment left, their farm decided to randomly choose 120 oranges and test their weights and found that they had a mean weight of 10.8 ounces. Because this was outside the acceptable range, they donated the entire truckload instead of selling the inferior oranges. So it's a lot of extra blah, 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 blah. But you should know that the 12.3 ounces is the parameter. Now, why is it a parameter? It is a parameter because it is the known weight of an orange. How do you know that? I don't know how you know that, but apparently it is. You know that. It is also a mean. The reason it is a mean is because it's not a yes/no question. You can't go up and go, "Hey, orange, how many ounces are you?" And they answer yes. That doesn't make any sense. Or I can't weigh an orange and go, yes. Yes what? What's the weigh? 10.8 ounces would be a statistic. And it's also a mean, obviously. And the reason it's a statistic is because it's a small sample of the overall population parameter. All right. The newest thing to annoy consumers is the use of robocalls in order to get people's personal information. The Correct Call company has implemented new software that first checks to see if the number is on the Do Not Call registry. Of the first 1,000 numbers checked, 81% were on the list. This is well within the norm since it is known that 82% of the people in the United States are on the list. So, the 81% is a statistic. Excuse me. Where's it? Oh, I'm on the wrong problem. 81, not statistic. It is a sample. And I should say proportion. It is a sample. Well, it is a statistic. I don't know what I'm saying. It is a statistic. It's not a proportion, but it is it is not a parameter. That's what I was getting at. It's not a parameter. See how you get your P words messed up a little bit? It is not a parameter because it is only from a sample. So it is a statistic, but it is a sample or a statistic of proportion. And our reason it's a proportion is yes, you're on the list. No, you're not on the list. That 82.5% is a parameter. Proportion. And again, it's a proportion because it's either on the list or not on the list. All right, there we go. Let's take a look at some examples. By the way, this first example I think is going to deal with means. We're going to take a look at it, but first I'm going to take a little break. All right, children, here we go. Here's an example. Hopefully, I would pause this, read it, just so you understand it, so I can fly through it pretty quickly. But the Rochester area always has the area trout and salmon derby. You know what? I haven't done any much fishing lately. I think they still do this. It always has thousands and thousands of entrants all over Lake Ontario. The derby rules are simple. Each entrant, now I made up these rules, by the way. Each entrant is only allowed to catch 5 fish, and they must be over 20 inches long, or they have to be thrown back. This way, they are only catching the mature fish. Miss Skinner is working on her IB dissertation, which is to study the effects of pollutants in the water and their effects on the population of salmon. Luckily for her, the derby fishermen do all the hard work. They get to catch the fish. She is just going to do some sampling. All she needs to do is randomly select fishermen, that's got to be a random sample, all across the lake. So she can't just pick one location. So let's assume she selected them randomly. She did a real nice job doing that. She painstakingly devised that plan. So she randomly collected the lengths of fishermen from various fish from fishermen across the lake. Her hard work paid off, and she was able to collect the lengths of 100 fishermen. So what I did on the next page was I just put, and I just made this stuff up. I put it in a, oh wow, that's kind of rough looking. So here's my sample of all the 100 collect. So so this would be fisherman 1. This information right here would be fisherman 1 right there. So fisherman 1's fish were 37.2, 42.5, 36.6, 39.9, 37.2. But I don't want to necessarily take all those. I just want them to give me the average of those 5 fish. And so what she decided to do was take the average of 5 fish. Now, the reason you want to take an average of 5, well, hold on, let's go back to the problem. So, her procedure was to measure the lengths of all 5 fish from the randomly selected fishermen and take their average. And this is going to become I thought I was going to say this, a topic for discussion later. It's important that you do this. And then just looking at the numbers on the table, well, if you just look at the numbers on the table, even those individual means, you really don't get an idea of what's going on until you actually generate it. So, like, you can look at all these numbers, and if you just look at this column, which is the average of what this last column is just the average of what the fishermen collected or caught. You still don't know what's going on. It's just human bodies can't look at numbers like that and go, oh, I get it, it's normally distributed, or it's not normally distributed. Well, this samples distribution, so what I did was I took all those numbers, I put them into a spreadsheet, and then I had the spreadsheet, and then I created a histogram. And the width of these things don't really matter that much. I used a decent size width of columns, and they all had to be uniform. So I guess it looks like I used a width size of about 2.4 inches or something to that effect. So, or length. Yeah, the widths of these are about 2.4, and this shows my distribution. So this is a sampling distribution where n equals 5, right? So it's not all the fish, it's the average of the fish collected. Notice the shape. The shape is approximately normal. So if I was to draw the normal distribution curve, I don't know, something to that effect, it's approximately normal. Notice we're a little bit bigger on this end, maybe not, though. Actually, it looks like we got a few, these columns, so it's approximately normal. And what we're going to find out is the larger the n value, the closer, the closer to normal we get. Because it sort of eliminates the irregularities. It eliminates the irregularities. So what do I mean by that? Well, let's say one fisherman caught 5 fish, and one of his fish was 50, or 60 inches long, which, probably wouldn't happen. But if it's 60 inches and you just took that one measurement, now your numbers are going to be all over the place. But if I take his 5 fish and I average his 5 fish, that's 60. If I take an average with the smaller fish, will be somewhat normal. Now, it'll be a little bit bigger, but it'll be somewhat in the middle, as opposed to just taking the 60 and then you got some numbers that are way on that end. If I take the average of those, it'll be somewhere around what is normal average. And if I take a whole lot of those samples and I spread them out, it becomes normal. You're going to get better at what I'm talking about there in a second. What I want to make sure, and I'm going to read this to you, I want to make sure you understand this to you. It's really important. It's really important what the size n is. So, for example, if I take 5 fish and I said this guy's 5 fish were 20, 21, 22, 23, and 60, and I average those up, well, this 60 has a pretty big effect on pulling the mean this way. But if, let's say, I did 30 of his fish, and they were all, 24, 22, 25, 28. Now this 60 is kind of spread out. It's like, okay, yeah, it's a 60, but because I now have a size of 30 that I'm taking, that 60 will get kind of spread out over 30 numbers, right? If you add a 60 to a bunch of smaller numbers, those smaller numbers are going to say, okay, you may draw me up a little bit, but you're not going to be, let me give you a really good example of it. Let me try this. Let me give you 3 numbers. I'm going to give you 2 numbers, 10 and 60. Well, let's do this. Let me do it to make it easier. Let's do 20 and 60. If I take the 2 numbers, 20 and 60, and I average those up, I average those to be, X bar would be 40. If I take 4 numbers and average them, 20, 22, 24, and 60, those averages would be, let me just add that up. Let's see, that's 20, 40, 60, 106. And you take 106 and you divide it by 4. 126. 126, and you divide it by 4. What is that, like 31? So you notice that this 60, yeah, it brought it up to 31, but it wasn't as drastic as 40, right? So yeah, it brings it up. So now if I have 30 of these, I got a big long list of 30 of these, this 60 will have very little effect. So that irregularity, that strange fish that you found, will get dissipated over a large number, and you'll get closer to the actual mean. And that's the idea of your sampling size n. The actual really important part is you take a large enough sample size n's. And once you get enough samples to see the contour, more samples, once you get enough samples that you get to see the idea of the contour of the shape, then more samples aren't going to, taking more and more and more samples aren't really going to improve things. You see, oh, there's the general shape. I can see what's going on. I don't need to take more samples, right? That's the idea of only doing enough samples instead of doing the population. Now, one thing you want to make sure, you can never, ever, ever understand what the actual sampling distribution looks like. Remember, the sampling distribution is all the samples of size n. You'll never get a picture on that because you're never going to do the whole thing. But you can look at a smaller number and get an idea and then say to yourself, how confident am I that the sample I did is close enough to the actual parameter? All right, so that's kind of what we're going to be talking about in this unit. We're going to be doing a lot of talking about that in this unit. Now, if you were to look back, you would say, okay, if I took sampling average lengths, those were sampling means. Those are statistics, and they're means. They're sampling means. Now I want to deal with, and we're going to deal with for the rest of the day, proportions. Yes, no questions. So we're going to flip some coins. But because we need to do it a lot of times, we're going to get the calculator to do the simulation for us. So this time we're going to use the calculator to simulate the coins. We're going to use this function of the calculator. Whether you have the TI Inspire or you have a TI-84, they both have this function called rand bin. It's right here. Rand bin. So if you go in your catalog and look for it. All right, so this is called a binary random generator. Now, why is it binary? Binary means 2, yes and no. That's it, yes and no. So this binary random, it only can be used for binary experiments that are going to have 2 outcomes, yes, no, boy, girl, blonde, not blonde. I didn't say blonde and redhead and brunette, and I said blonde and not blonde. Senior, not a senior. Driving a car, not driving a car. So it can't be used for means. It can only be used for proportions. Okay, and that's what we're going to be dealing with today. So let's say I put in my calculator rand bin 20 comma 0.5. Now let's talk about what that looks like. So if you go into calculator mode and I go into the catalog and I find, I'm going to just type in rand, R for rand for R's, and I got to find rand bin. All right, so rand just gives you a random number, but rand bin, so what I'm going to do is, what did I say, 20 comma 0.5. Now what that's going to return is 20 is the number of trials. So what I just did was simulate flipping a coin 10 times. 0.5 is the probability of whatever you're testing. So in this case, so what I want to test is it returns a number of heads or tails. So what I'm going to say is whatever number I get is the number of heads. Now, because the probability is 0.5, I should get 10 heads and 10 tails. Well, the first time I got 10. Oh, I got 10 over here too. It might get lucky. I bet if I get these same numbers, I'll talk about that in a second. So what I can do, so what that is that's like you flipping 20 times and you got 10. The person next to you is going to flip 20 times. They're probably not going to get 10. So let's see. I'll just press enter. Yeah. Oh, yeah, it's going to be 8, 9. This is why, notice how these numbers here match the ones on my example. This is why a calculator is not always truly a random sample, because the way it works, and it's a whole different discussion on good computer programming. This was poorly programmed so that it returns these numbers. But in general, it does a pretty good job of giving us some random numbers. So we'll use rand bin. I go through and I say, oh, the first time I got 10 heads. The second time I got 11 heads. Then I got 12 heads. Then I got 8 heads. And then I got 9 heads. Now, if I did that forever, I would get close to what I know the answer is. The answer is 10. I would get close to 10 heads. Not exactly, but I would get close. Now, what I want to do is take a proportion of all those. So, let's do this again. Let me clear this out. Control tab, control menu, and I press enter. But what I want to do is, remember, the proportion is, and do I say it here? A proportion is the number of yes-nos over my total. So let's see what I got here. Oh crap. Menu. I'm just gonna 20 comma 0.5. All right, stop. All right, 13. So in this case, I would have 13 out of 20. Now 13 out of 20 is 0.65. Or I can just do 13 divided by 20, and it gives me 0.65. Do it again. 6. Oh, 6. 6 out of 20. That would be 0.3. This was pretty close to 0.5. This wasn't close at all. 11. All right, so now I've gotten 2 that are higher. 0.55. One that's lower, another one that's higher. So you'll notice this one would sort of be an irregularity. But if I did this 100 times, that irregularity would be kind of washed out. It would be watered down how radical that irregularity is. And eventually I would get closer and closer and closer to what the theoretical probability of flipping a coin is. So actually, in a perfect world with an infinite number of trials, you would expect to see the probability near 0.5. That is called the theoretical probability. It's what we know to be true, but it doesn't always happen. Now, doing this over and over again would be very time consuming. There's a better way. And what we're going to do on the next page is we're going to do 20 flips of a coin. Now notice how I did 20 flips of a coin, took an average, 20 flips of a coin, took an average, 20 flips of a coin, took an average. That would take me forever. So we're going to do the little bit better and faster way. So what we're going to do is we're going to just adjust it, and we're going to add this 10 on. So this will be 10 times the 20 flips. So it's like you flipped the coin 20 times, took an average, took the coin, or figured out how many heads there were. Took the coin 20 times, found out how many heads there were. Took the coin 20 times, had how many heads there were. But you did it 10 times quickly. So notice if I do that, then I get 12 heads, 10, 11 heads, 6 heads, 9 heads, 13 heads, 9 heads, 11, 12, 13, so on and so forth. And that's very easy to do in the calculator. You just do the same function, but we're going to put a comma, and we're going to do it 10 times. Boom, there they are. Those are the 10 flips of the coin. Those were 20, that in this one, 10 out of 20, 9 out of 20, 8 out of 20, 6 out of 20, 11 out of 20, 7 out of 20. If I took, so these are my sample size of 20, and I did 10 of them. So my N was 20, and I took 10 samples. And I can, and then I can do that all day. I can just get the calculator to do that forever and ever and ever. So, but again, it's kind of useless to look at until you look at it graphically. So what we're going to do is just really quickly put this into our calculator, a list of 10. So what we're going to do is we're going to come over to our calculator. We're going to go into calculators, and what do I call this? Flips. I call it flips. Flips. And I want this to be equal to, we're just going to rand bin. So notice how it says equals. It's hard to see there. I'm going to put these in and I'll expand it for you. 20, comma, 0.5, comma, 10. And what that's going to do is it's going to fill the first 10 columns with that function. So instead of just putting them in a list on the screen like this did here, it puts them in it puts them in a spreadsheet. Well, what can I do with that then? Well, what I can do with that is simply create a dot plot or a histogram of what's going on. So let's do that. So let's go quickly into, let's go menu, insert. Yeah, menu. Oh, yeah, menu, statistics. No, what am I doing? Oh, you click on doc. Jeez. Sorry, a little brain cramp. Going to doc, insert, data and statistics. And there, that's weird stuff. Just click on the bottom and click flips. So notice, wow, now that doesn't look like what I came up with here. But notice, well, okay, I would expect this to be centered at about 10. And it's kind of around 10. Maybe let's turn it into a histogram. So I'll go into menu, plot type, and I'll go histogram. Okay, that looks a little bit better. That looks like it's sort of centered around 10. So I got these ones way off here to the left, but I got the bulk of mine over here, so it's kind of centered around 10. And I would expect to see it centered around 10. If I did 20 flips of a coin, approximately 10 would be heads. Well, that's not a great looking distribution. That's not overly useful. So what would happen if we did it 100 times? So instead of, we're going to flip the coin 20 times, but now we're going to do it 100 times of 20 flippings. So let's change that. We'll change this distribution. Let's just close this out. I'll just close this out. And we'll do it again. So I'll call it flips again. And I'm going to say, bam, rand bin, 20, comma, 0.5, comma. Now I'm going to do it 100 times. So it's the same function, except for now I'm not doing it 10. So that's as if 100 students flipped the coin 20 times, and now we're going to plot the 100 students. So the irregularities of those kids that got only 3 heads or those kids that got 18 heads are going to be watered down by all the other kids. Now we'll go into doc, insert, data and statistics, and now you see a lot more dots, right? You should see 100 dots. We'll click on this and we'll go flips. Notice now how many 10s there are. Sure, one kid only got 5 heads. 2 kids got 16 heads, but it's centered around 10. If we change this to a histogram, because histograms give us a real good idea of what shape we have is, you'll see that, wow, it's becoming more and more normal. It looks a lot like that, actually. Looking pretty close. Not quite the same, but close. And let's do this. No, let's not. I think I'm going to do it later. We'll do that a little bit later. Okay, so let's look at sampling variability. So let's look at another example. Let's suppose the United States, I'll come back. I need to pause and save this. Okay, let's take a look at another example. In order to save time for you, maybe pause this and read through it. But it says the United States wants to see the population about legalizing marijuana, especially since now we just found out that Canada decided to make it legal to have a certain amount. So the survey asked a nationwide sample of 2,500 adults and were asked about their feelings around legalized sale of marijuana. 70%, of the respondents, 1,750, or 70%, said they don't agree with legalizing it. Okay, so this is our sample of 2,500, 1,750, or 70% said they don't agree with legalizing it. So the number 70% is a statistic, right? It's not a parameter. It is a statistic because it is only of a very small sample. 2,500, by the way, is a huge sample of the general population. And our population in this case would probably be people of smoking age. The parameter, recall, deals with the entire population. And that would be the percent of all Americans over the age of 18 that would agree or disagree with legalizing marijuana. But that would be impossible to test. And you never could possibly know it. So what we're going to assume is our p-hat. Remember, our p-hat is our sampling proportion. This is our sampling proportion. It is a statistic. Okay? It's our sample proportion as opposed to our population proportion. So the other thing is, you're going to find out that is 2,500 enough to test? And of the over 200 million people, is that big enough? And if we take and someone could say, well, I could do another sample and do another 2,500 and I'll get a different answer for p-hat. Yeah, you will. And that's why we're talking about what's called sampling variability. You could do a sample of 2,500 and I can do a sample of 2,500. Will they be exact? They won't be exact. Will they be close? They'll probably be pretty close. 2,500 is a ginormous number in the world of statistics, especially if the population is known to be normally distributed. So these statistics are going to vary with repeated samplings, but they will give you an overall look at what the actual population is. And 2,500 is a big enough number that we should be able to get an idea of what's going on and be pretty accurate. And then if we took all of those samples and combined them, right, that would be what we called earlier the sampling distribution. All the possibilities of size 2,500. Let's keep going. We're going to use the computer to simulate drawing samples, simple random samples of size 100 from the population of all students age 18 and older from the United States of 200 million residents. Let's say that 70% is in fact the true percentage of Americans that believe legalizing marijuana would be a bad idea. In other words, the parameter P, again, here's our population parameter P, would be 0.7. Now, are we going to know that it's 0.7? We'll never know what that is. We never can know what that is, but we can get close. Of course, and the other thing is, if I already knew what the population parameter was, why would I bother doing any statistics, right? So if I already know it to be 0.7, why would I bother doing any statistics on this at all? But for this purposes, we're going to assume we do know it. Later on, I'll show you what we're going to do if we don't know what it is. All right, so procedure. We're going to assign the numbers 0 to 6 to stand for people who disagree with legalizing marijuana, And the numbers 7 through 9 would represent all those that agree with legalizing it. Do I have that chart in here? So I don't have my random, so I'll be right back. Okay, so our procedure is going to be to assign the numbers 0 to 6. Now, why is it 0 to 6? Because that's 7 numbers for the people that disagree. And the numbers 7 through 9, or 7, 8, and 9, to the people that agree. So these are the people that agree. Now, why did I pick that? Well, because we said we know that our population is known to be 0.7 disagree. So instead of it being a 50-50 like the coin flip, now it's 0.7. And what we're going to use is we're going to use a random number table. So if I get a 0, that's an agree. That's a disagree. If I get a 5, that's a disagree. So what I would do then is come over to my table, and I'll have a random number table in your homework, and I say, okay, I have an 8. So if I go here to disagree or agree, so 8, that's an agree, because that's 7, 8, or 9. 0, that's a disagree. 9, that's a agree. 4, that's a disagree. 2, disagree. 5, disagree. 2, disagree. 5, disagree. 8, agree. So, and I just found this random table online, right? So I'll just go through, and I want to do that 100 times. So what this is since this is a random number table, this is like going out to the population. Where am I going? Oh, I just got to click here. This is like going out to the population. Why am I at this page? And randomly asking 100 people. So, okay, let's assume I did that. I can now use a random number table to ask 100 people from the population. So let's assume that I went through 100 people on that table, and I asked them. So now my statistic p hat for the proportion from 0 to 7s in the sample. Instead of doing this, I used Microsoft Excel. And I simulated 100, and I repeated this 1,000 times. So you can imagine I'm not going to come over to this table. I'm not going to go over this table and go do it 100 times, and then do it 100 times, and do it 100 times, do it 100 times, do it 100 times, do it 100 times, do it 100 times. And then I want to do that 1,000 times? Oh my gosh, I would be there all day. I keep forgetting to go back like this. So what I did was I did it for me. So I used n size 100, and I repeated it 1,000 times. Now, a few of those times I got some small numbers, but notice that the bulk of mine is around 0.7, which is what I would expect it to be. And it's fairly normally distributed, right? Because my size n was large enough. And I did it enough. I took enough samples of size. Samples of size n. Okay. So I noticed what I noticed. I'm going to tell you what you noticed. You notice the sample appears to be approximately normal, normally distributed. With, or how about this, centered around 0.7, which is which is what we expected. Now, had I only done sample size of 2 and I did it 5 times, I could have some weird stuff. But because my n was large enough and I took enough samples, I can get a fairly good, accurate look at what this thing looks like. So a sampling distribution is a probability distribution of a sample space. Now remember, sample space is all possible outcomes, right? A list of all possible outcomes. Sample space statistic based on all simple random samples. SRS, simple random sample, just means you collected the data randomly. You did a good job of collecting the data. And then of all the same sample size, of all same sample size. So in this case, in this case, N. In this particular case, our sample size was N. Our sample size was 100. We used 100. And this is what we got. We got this distribution. Now, notice they range from 0.58 all the way to 8.5. So if this is normally distributed, what would be my standard deviation? Where would I expect, how spread out is this data? From 0.5, I don't know if there's anything here. This might be 0.5. It looks like maybe 0.55 to 8.5. So that's like a spread of 0.30 on this distribution. So our sampling distribution is a distribution of all the different statistics of all the different simple random samples of size 100. In this case, what would I do if now, instead of using 100, now I ask 2,500, and I do it 1,000 times. So I go over to this table, and I go to first 2,500 numbers, and I take an average. And then I do another 2,500, and I take an average. And I do another 2,500 and take an average. What would happen? Well, let's take a look at the sampling distribution. Now notice I'm using the exact same scale as I did before. 0.55 to 0.85. But now, because my N value is 2,500, look what's going on. All of those values are between 0.7 and 0.730. So instead of being spread out from here to here, it's only spread out from here to here. Now, why is that? That is because my sample was 2,500, any irregularities, instead of getting washed out over 100, now got washed out over 2,500. They get watered down like crazy. It's like if you had one really loud, obnoxious person in a class of 30, right? They would be obnoxious, right? They would drag out they would increase the obnoxious level in the room. But if you took that same obnoxious person, that same irregularity, and you put them in a class of 200, or then they would get watered down. You wouldn't hear them as much. You could get away from them. You wouldn't hear them as much. But if you take that same person and you put them in a room of 2,500, they're so watered down, you'd never even hear it. Well, that's the same thing that's going on here. Even in those sample size of 100, because they got so watered down, they decreased the overall spread of the distribution. They were watered down over 2,500, so they decreased the spread. Now, if I take this thing and I take just this piece and spread it out so that I can actually see what it really looks like, instead of saying, okay, it's all crunched up here. So I'm really only going to go from like 0.67 to maybe 0.76. I'm not even sure what it goes. Let's take a look. We're going to actually, this does not look normal, right? I want to point out that this does not look normal. It is centered around 0.5, centered around 0.7, but it doesn't look normal at all. But notice I use that same graph. The only reason that's true is because I used the same scale, the same X scale as I used on the one before it. Now what we're going to do is we're going to spread this out. So we're going to take this corner and we're going to pull it that way, and we're going to take this corner and we're going to pull it this way, and we're going to see what does this distribution actually look like. Oh. Wow, that really looks normal. Look how normal that thing is. It's really normal. 100% of the data is between here and here, or between 0.675 and 0.73. 100% of the data is between those two numbers. And all we did was increase n to 2,500. Up here, 100% of my data, when n was 100, was between 0.55 and 0.85. Now remember, we're going to divide that. Remember, if we go out 3 standard deviations, 1, 2, 3, 1, 2, 3. So we got 3. So if I take this 30 and divide it by 6, that means my standard deviation is probably somewhere around 0.05. If I take this one, and what is this difference? Let's just make this an 8. So that's that's 0.05, and if I divide by 6, well, that's really tiny. 0.001, I don't know what that is. Let's look. 0.05 divided by 6. 0.08 as opposed to 0.5. This should be 0.5. 0.5. So, crazy. It's so much the standard deviation. So by increasing my n value, my standard deviation got smaller. Now, if your standard deviation is smaller, you can make better, more accurate predictions. So the larger your size n, and this is the kind of things I want you to put on that bottom, the larger the n, by moving that n value to 2,500, our data got less spread out. In other words, it got more accurate. In other words, the irregularities, that loud, obnoxious person got watered down, over time. So again, remember what I always tell you. Statistics are unpredictable in the short term, but in the large term, the truth is revealed. So by taking 100, okay, it's unpredictable a little bit, but by taking 2,500, like, wow, look how accurate it is. And I can even shrink this more by taking more samples, and I can shrink it more by taking more samples, and a larger n, and a larger n, and a larger n. As a matter of fact, if I changed n to equal the population, it wouldn't be spread out at all. I would know what the answer is. It would just be right there. But, again, I don't want to do the population. I only want to do a sample. All right, that's it, kids. That is all she wrote. I hope day 1 was sort of okay for you. Hit the subscribe button, hit the like button, stay with it. We're going to be spending a lot of time talking about this. All right? Goodbye.